Okay, so today I'm going to prove the fundamental theorem of arithmetic using the principle of complete induction. Okay, the fundamental theorem of arithmetic states that every integer n greater than 1 is either prime or a product of primes. So we're going to do this by induction. Okay, so we're going to have our base step, right? So let's look at the next integer after 1, which is 2. S of 2 states that 2 is either prime or a product of primes. And this is clearly true, right? Okay, S of 2 is true because 2 is prime, right? We can see that S of 3 is true. S of 4 is true because S of 4 states that 4 is either prime or a product of primes. 4 is a product of primes. And we could see that this would be true indefinitely. So let's go ahead and move on to the induction step. Okay, let k be greater than 2 and assume that S of 2 is true, S of 3 is true, all the way to S of k minus 1. And we're going to assume that all of these are true, right? Okay. Remember, with complete induction, you assume that all the previous terms are true. And from that, if you can show that for the kth term it's true, then that it'll be true for any arbitrary integer you choose, right? Okay. So we have two cases. So case one is if k is prime, right? Because natural numbers are either prime or composite. So the first case is where k is prime. But if k is prime, right? If k is prime, then S of k is true, obviously, because k is prime or a product of primes, right? Let's go ahead and move on to the second case. So case 2, when it's composite. So k is composite. So if k is composite, then the definition is k is equal to a times b, where a and b are integers. And of course, and also, a is strictly between 1, well, strictly, right? Strictly between 1 and k. And same with b, right? Okay. Because of course, if k is equal to a times b, then a must be strictly between 1 and k. It can't be k, right? Okay. And then same with b. They have to strictly be between these two. Okay. All right. So, by the inductive hypothesis, which stated that S of 2, S of 3, all the terms between 2 and k minus 1, right, are prime or a product of primes, right? We know that S of A and S of B are true, basically saying that A is a prime or product of prime and B is a prime or product of prime, a product of primes. So by the inductive hypothesis, S of A and S of B are true. Okay? This means that A and B are prime or a product of primes, right? So let's say this. Say A is equal to P1, P2 dot 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 P sub R, and P is equal to Q1 Q2 dot 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 Q sub S, right? Where P sub I and Q sub J, right? Q sub J are primes for every I between 1 and R, right? And J between 1 and S, right? This is basically saying that all these are prime and all these are prime, right? Okay. So, thus, K is equal to A times B because it's composite, right? And we can substitute. That means that this is equal to P sub 1, P sub 2, P sub R times Q sub 1, Q sub 2, Q sub S. And look at that. K is a product of primes, right? Okay. So this shows, which shows that K is a product of primes, right? Okay, so this implies that S of K is true. Basically, K is a prime, which was for the first case, right? Case 1. Or for the second case, K is composite, we showed that K was a product of primes, right? So we showed that it worked for K, assuming that it worked for all the previous terms. So that means by complete induction, we know that the statement every integer n greater than 1 is either prime or product of primes is true, regardless of what integer you choose. Okay? So Q, B,